following on from the previous video, we were trying to understand why the root test works. So you would try and investigate a series. Well, if you compute this value of that series, if this value is less than 1, then the original series that you're trying to investigate will converge. So we're going to try and understand why that's the case. So start out with this. So this can be rewritten as this. So for a limit of this thing here to exist, remember the true definition of a limit. For a limit of this thing here, so that's this thing here. For a limit of this thing to exist, it would mean that for all n beyond m, it must lie within any given small tolerance. Okay, so for all n beyond m, everything must lie within this region here. Okay, so we would start out with this, and then incorporate the true definition of a limit. That will then take us to here. Okay, so we start here. For the limit of this thing here to exist, it would mean that for all n beyond capital M, it must lie within this region here. Remember, from M all the way to here. We don't care what happens prior to that. We only care from M to here. So you can see that an to the power of 1 over n must lie within this region here. So you can actually say, so this is your limit here, and then for a small tolerance. So this tolerance could be a very, very small number. It could be any small, however small you want it to be. It's going to be a very, very small number. So hang on, let me think. So starting from here, incorporate the true definition of limits. That would make this statement to be true. Because look at this. This thing here is this thing here. It must always be less than your limit. Less than your limit plus a small tolerance, So from here, incorporate the true definition of a limit. That will then make this statement to be true. So this statement will be true for all n beyond capital M. So we are currently here. So when you're reading the proof, that would be this statement here. So Ran to the power of 1 over n, which is this thing here, is always less than this thing here for all n beyond capital M. Okay, so this so we are currently here at the moment. When you come to read the proof, that would take you to here. Okay, so from here, power equally to both sides, powered by n. So this thing here to the power of n, and then this thing here to the power of n. This times this will be 1. So basically from here, that will then take you to here. So that means that, remember, this line here represents an to the power of 1 over n. But then now we have the sequence itself. So you cannot imagine this to represent this. So this graph here represents this. It represents this. But now we have the sequence itself. Okay, so hang on. So when you come to read the proof, that would be this statement here. Okay, so now hang on. Let me think. So we are currently here at the moment. We are currently here. So remember, if you have 0, 1, and then any number below 1, the geometric series. Let's say if a and then Rn, and then for n equals 1 to infinity. This geometric series we've seen many times, and I asked you in the past to accept that this will converge, and we've proved it. This will converge. Well, if R here is less than 1, it's going to converge. So let's take the case where A is 1. So this geometric series here will converge. N equals 1, infinity. This geometric series here will converge. Well, if you look at this here, if R, so 0 to 1, if this is our r here is less than 1. So if you look at this, hang on. If you look at this, hang on. So if you look at this, remember for it to have a limit of rho, so that's this bit here. The statement is saying if rho is less than 1, if rho is less than 1, so hang on. So this is your 1 here. This is your level 1. Rho will be less than 1. Now, if rho is less than 1, you can always select a tolerance. That's always between rho and 1. Because, for example, let's just say the limit is 0.99. It has to be lower than 1. 9997, say. So this is your limit here. But what I can always select a number between rho and 1. I can always select 0.99998. Now that's between rho and 1. So the point is that, hang on, we were currently here. We were currently here, which is the same as this bit here. The point is that this thing here, hang on, 0, 1. This is your limit here, rho, and then this is your rho plus epsilon. You see, this here is really r to the power of n, where r is less than 1. You can call this level here rho plus epsilon, which is this thing here, or you can call it r. So now if you assign this name here, r here, and then